theory. In this lecture, we will be talking about Thevenin's and Norton's theorem. Okay. So the premise or starting point of both Thevenin's theorem and Norton's theorem are the same. It is about representing a network. So what should be the nature of the network? It should be linear, active, and bilateral, and it should have some sort of sources and loads. Okay. And the other thing is that if we want to apply this theorem, we should have a defined open terminal. Okay. So such a network, that is any linear active bilateral network consisting of a number of sources, resistances, etc., with open terminals defined, can be converted into a simple network consisting of, that is, let me just draw, that is, we have a network having the aforementioned properties, and we have two terminals defined in them. Let's call them A and B. It can be converted into a simple network consisting of a voltage source in series with the resistance, right? This is A, this is B, a voltage source in series with the resistance. This we call Thevenin voltage, and this we call as Thevenin resistance. This is Thevenin's theorem. This is Thevenin's theorem, and this is called as Thevenin equivalent network or circuit. Okay, equivalent Thevenin circuit or Thevenin equivalent circuit. Right. The same thing, the same network again, it can be represented as a current source in parallel with a resistance. We call this Rn for R Norton, and we call this In for I Norton. So this will be Norton equivalent circuit. So this is Norton's theorem, right? So this can be converted into a simple network consisting of one, a voltage source in series with resistance. This would be your Thevenin's theorem. Okay. Or a current source in parallel with resistance. This would be your Norton's theorem. So if you look at it, this Thevenin's theorem and Norton's theorem are duals of each other, and these circuits, if you have your Thevenin circuit, you can get your Norton equivalent circuit from that itself, because they are duals of each other. You can simply use a source transformation between them. Okay. So now let's see how we can identify this, right? Or like this is just the theory, like the theory just states that, okay, or the theorem just states that, okay, it is possible to do this. It's possible to represent any network having certain properties in such and such form. So our problem is how do we do that? Okay. So again, let's we have our network and we have our terminals A and B defined. Okay. And we have our equivalent Thevenin circuit, right, RTH. We have our equivalent this one, voltage VTH. We also have our equivalent Norton circuit. Okay. Again, IN and RN, A and B. Okay. So the response of this network across A and B should be the same as the response that we get from this actual original network, right? So if we keep this terminal open, right, if we keep this terminal open and we measure the voltage across this terminal, what will it be? It will be VTH, right? It will be VTH. Therefore, to find VTH, what we do is that we keep the terminal of the network, any network or any terminal that we want to find, the Thevenin equivalent, we keep it open and we measure the open circuit voltage. That will be equal to the Thevenin equivalent voltage VTH. That is VTH equal to V open circuit across whichever terminal that we want to find. Okay. Now coming here, suppose we short circuit this, okay, and we measure the current across, current flowing through this terminal. What will it be? Because this is short circuited, it will bypass RN and the whole IN will flow through this. So the same thing should happen here also, right? That is, if we short this here, some current will flow through here, right? Let's call it I short circuit. That should be equivalent to IN. In fact, it should be. That is how we find out IN. That is, I Norton is equal to I short circuit. That is, suppose we have a network, right? We have defined terminals A and B and we want to find the Thevenin equivalent or Norton equivalent circuits. So how do we find the Thevenin voltage? We keep that terminal open and we find the open circuit voltage across that terminal and we call it the Thevenin voltage. And how do we find the Norton current? We short that circuit, terminal, we short circuit that terminal and then we find the current flowing through that terminal. That is the short circuit current, ISC. That will be equivalent to the Norton resistance, Norton current. Now we have to find two things, right? RN and RTH. So in fact, for any network, how do you find the resistance across any terminal? How is it defined? It is defined as resistance V equal to IR, R equal to V by I, right? Again, for the same thing happens here. We have to find the ratio of voltage to current across this terminal. That is how we find the resistance. So it so happens that, and we also mentioned that we can transform these two. Source transformation is possible. From this, so one thing that you should be able to identify is that Rn equal to Rth equal to Vth or V open circuit. Let me just rewrite it. V open circuit by ISC. Okay. So we have Vth defined as open circuit voltage, IN defined as the short circuit current, and Rn which is equal to Rth, which is the open circuit current, open circuit voltage divided by the short circuit current. Okay. This holds true for all circuits. Again, this also holds true for all circuit. This also holds true for all circuit, but we don't use this formula all the time. Because suppose if you are just asked to find the Thevenin equivalent, just the Thevenin equivalent circuit of any given network, then you need not find the Norton current. Okay, you have the Thevenin voltage. Then what we do is that depending on the type of the circuit, we may find ISC, or we can directly find RI or RTH, whichever. Okay, so let's see how we can do that. So internal structure or types of the sources within the circuit or network that we are given, and the problems that we encounter can be classified into three. Okay, so let's say category 1, only independent sources. Okay, so here to find Rn or Rt, what we do is that we simply suppress the sources and find equivalent resistance. Right, we simply suppress the sources and find the equivalent resistance across given terminal. Right, that is category 1. For category 2, we have both independent and dependent sources. What do we do then? Here what we cannot suppress what you say this dependent sources we cannot suppress, right? We cannot simply suppress and find the equivalent resistance. So what we do is that Rn and Rth we find by find V open circuit, I short circuit, and then we take Rn equal to Rth as V open circuit by I short circuit. That is, we will have to go for the basic definition, right? Here this is easy because you can just suppress and find the equivalent resistance, but here it is not. Here we will have to use the actual definition, V open circuit by I short circuit. Then category 3, here it becomes a little bit tricky because only dependent sources. The thing with dependent sources is that it is a voltage controlled or current controlled source, and for it to act we need to energize it somehow, and only if we energize the dependent source somehow we'll identify what is the response it is having. So within a circuit any source will have some sort of response everywhere, right? To find the resistance RTH and RN for a circuit having only dependent sources, we cannot obviously we cannot suppress the source, and we cannot, the problem is that we cannot directly use this definition because we don't know we don't have any independent sources within the circuit to energize the dependent source. So what we do is that we apply an external source and then find voltage to current ratio at the terminal, right. Here also it is defined as voltage to current ratio, current resistance anyway. Here the thing is that since there is no internal independent sources to excite the dependent source and get its response at the open terminal or the defined terminal, what we do is that we ourselves put a source, a predefined independent source, so that we can get the response, right, and that response we will take as the resistance across that terminal. So these are the three types of problems in this let's say theorem that we have that we'll discuss in the next lecture. Thank you.